Hydrogen embrittlement or heat damage mechanisms as a part of environment-assisted cracking. Description of hydrogen embrittlement damage mechanisms based on API 571. A loss in ductility of high-strength steels due to the penetration of atomic hydrogen can lead to brittle cracking. Hydrogen embrittlement can occur during manufacturing, welding, or from services that can charge hydrogen into the steel in an aqueous, corrosive, or a gaseous environment. Here's a comprehensive, detailed description of hydrogen embrittlement or heat damage. Introduction. Hydrogen embrittlement is a form of material degradation where metals, particularly high-strength steels, alloys, and certain non-ferrous metals, suffer from a loss of ductility and toughness due to the ingress and interaction of atomic hydrogen within their microstructure. This process can lead to sudden, often catastrophic, failure of components during service. Fundamental of hydrogen embrittlement. Number 1 is nature of hydrogen in metals, includes, for atomic hydrogen, the smallest and most mobile form of hydrogen atoms that can penetrate metals. For sources of hydrogen, includes, manufacturing processes, such as welding, electroplating, pickling, corrosion reactions, such as cathodic reactions releasing hydrogen, environmental exposure, such as hydrogen gas atmospheres, operational conditions, such as high-pressure hydrogen environments. Number 2 of fundamental of hydrogen embrittlement is pathways for hydrogen entry, diffusion through the metal lattice driven by concentration gradients, entry via surface defects, microcracks, or porosity, transport along grain boundaries, dislocations, or inclusions. Mechanisms of hydrogen embrittlement. Hydrogen embrittlement occurs through complex microscopic mechanisms, which are still areas of active research. Some leading models include, number 1 is hydrogen-enhanced localized plasticity or HELP. Hydrogen increases dislocation mobility, leading to localized plastic deformation at lower stresses, which facilitates crack initiation. Number 2 is hydrogen-induced decoherence. Hydrogen-enhanced decohesion. Hydrogen accumulation weakens atomic bonds, especially at grain boundaries, leading to reduced cohesive strength and facilitating intergranular fracture. Number 3 is hydride formation. In some materials, such as titanium, zirconium, hydrogen reacts to form brittle hydride phases that promote cracking. Number 4, internal stress and crack initiation. Hydrogen can cause internal pressures within microvoids or along inclusions, initiating microcracks. It also reduces the energy required for crack propagation. Types of hydrogen embrittlement includes, number 1, delayed hydrogen cracking. Occurs after processing or exposure, often under sustained load, with cracks developing after a delay period. Number 2, stress corrosion cracking, SCC, with hydrogen involvement. Combined effects of tensile stress, corrosive environment, and hydrogen presence lead to crack growth. Number 3, hydrogen-induced blistering. Formation of blisters or bubbles beneath the surface due to hydrogen accumulation, leading to surface flaking. Materials susceptible to hydrogen embrittlement includes, number 1 is high-strength steels and alloys, such as martensitic steels, tool steels. Number 2 is titanium and zirconium alloys, hydride formation. Number 3 is aluminum alloys, less prone but still susceptible under certain conditions. Number 4 is nickel-based superalloys. Number 5 is brittle or high-strength non-ferrous metals. Materials with high strength, low ductility, or specific microstructures are especially vulnerable. Manifestations of heat damage includes, number 1, reduced ductility and toughness, evidenced by decreased elongation and impact resistance. Number 2, microcracks and microvoids, often initiating at inclusions, grain boundaries, or surface defects. Number 3, intergranular or transgranular fracture modes. Number 4, surface blistering or flaking. Number 5, sudden failure under nominal or low stress conditions. Factors influencing hydrogen embrittlement includes, number 1, hydrogen concentration factors resulting the impact higher levels increase risk. Number 2, stress level factors resulting the impact higher tensile stresses accelerate damage. Number 3, temperature factors resulting the impact certain temperature ranges promote hydrogen ingress and mobility. Number 4, material microstructure factors resulting the impact microstructures with high dislocation density or microvoids are more susceptible. Number 5. Environment factors resulting the impact presence of moisture, acids, or cathodic protection systems can generate hydrogen. Number 6. Processing history factors resulting the impact welding, surface treatments, and prior mechanical work influence susceptibility. Detection and evaluation of heat damage includes, number 1 is using visual inspection method, surface blistering or flaking. Number 2 is using microstructural analysis method, microscopy to identify microcracks, hydrides, or blistering. Number 3 is using fractography method, fracture surface examination revealing intergranular or transgranular features characteristic of He. Number 4 is using hydrogen measurements method, techniques like thermal desorption spectroscopy, TDS, to quantify absorbed hydrogen. Number 5 is using non-destructive testing method, includes ultrasonic testing, to detect internal cracks, acoustic emission, to monitor active crack growth, electrochemical methods, to measure hydrogen flux. Prevention and mitigation strategies includes, number 1, use of alloys with low hydrogen affinity. Number 2, applying post-weld heat treatments to reduce residual stresses and hydrogen content. Number 3, employing coatings or barriers to prevent hydrogen ingress. Number 4, controlling environmental exposure, such as avoiding cathodic protection in susceptible environments. Number 5, designing components to operate below critical stress levels. Number 6, regular inspection and monitoring. For early detection. Hydrogen embrittlement is a serious degradation mechanism that compromises the integrity of metallic components exposed to hydrogen-rich environments. It stems from hydrogen atoms diffusing into the microstructure, weakening atomic bonds, and promoting crack initiation and propagation. The damage manifests as microcracks, blistering, and sudden brittle failure, often with little warning. Understanding the mechanisms, factors influencing HE, and employing appropriate inspection and mitigation strategies are essential to ensure the safe and reliable operation of hydrogen-exposed metallic structures. Hydrogen embrittlement affected materials based on API 571, carbon steel and low alloy steels, 400 series SS, precipitation hardenable, pH, SS and some high-strength nickel-base alloys. Here's a detailed explanation of the materials affected by hydrogen embrittlement, He, including the properties that make them susceptible and specific examples. Hydrogen embrittlement can compromise a wide range of metals and alloys, especially those with certain microstructural characteristics or high strength levels. The susceptibility depends on factors such as microstructure, mechanical properties, and environmental exposure. General characteristics of susceptible materials includes high strength, high hardness metals and alloys. Elevated strength levels often correlate with increased susceptibility because of the microstructural features such as dislocation density and microvoids. Brittle or low ductility materials. Materials that inherently lack toughness are more prone to crack initiation and propagation under hydrogen influence. Metals with microstructures that facilitate hydrogen diffusion or trapping. Fine-grained, high dislocation density, or microvoid-rich microstructures tend to trap hydrogen more readily. Specific materials affected by hydrogen embrittlement, He. Number 1 is high-strength steels, includes, martensitic steels such as hardenable, high-carbon steels, austenitic steels, susceptible when cold-worked or in certain microstructures, spring steels and high-tensile steels such as 4340, 300M, CRMO steels, chromium-molybdenum alloys. Steel's susceptibility factors, includes, elevated tensile strength greater than 1000 MPa, residual stresses from welding or processing, microstructural features like microvoids, inclusions, or grain boundaries. Number 2 of specific materials affected by hydrogen embrittlement is titanium and titanium alloys, including titanium grade 2, grade 5, etc., forms brittle hydrides upon hydrogen absorption, used extensively in aerospace, chemical processing, and biomedical applications. Titanium susceptibility factors, includes, hydride formation causes embrittlement and cracking. Sensitive to hydrogen ingress during welding or corrosion. Number 3 of specific materials affected by hydrogen embrittlement is aluminum and aluminum alloys, includes, certain high-strength aluminum alloys such as 2024, 7075, less susceptible than steels, but hydrogen can cause blistering or cracking, especially under tensile stress. aluminum and aluminum alloys mechanisms. Hydrogen promotes intergranular or transgranular cracking in microstructurally vulnerable alloys. Number 4 of specific materials affected by hydrogen embrittlement is nickel and nickel-based alloys, includes, Inconel, Monel, Hastelloy, used in high-temperature or corrosive environments, susceptible to hydrogen-induced cracking, especially during welding or high-pressure hydrogen service. Number 5 of specific materials affected by hydrogen embrittlement is non-ferrous metals, includes, number A, zirconium and zirconium alloys, widely used in nuclear reactors. Hydride formation leads to embrittlement. Non-ferrous metals. Number B is copper and copper alloys, generally less susceptible, but hydrogen can cause blistering or cracking in certain conditions. Number 6 of specific materials affected by hydrogen embrittlement is other metals and alloys, includes, number A, brittle or very high-strength materials, such as certain ceramics or composites, though not metals. Some ceramic metal composites can be affected. Number B, certain stainless steels, especially those with high residual stresses or microstructural vulnerabilities. Factors contributing to material susceptibility includes, number 1, high strength and hardness. Materials with tensile strengths above 1000 MPa are more vulnerable. Number 2, microstructure, microvoids, inclusions, grain boundaries, dislocations, and prior processing features can trap hydrogen. Number 3, environmental exposure. Presence of hydrogen-generating environments such as cathodic protection, corrosion, or hydrogen gas atmospheres. Number 4, manufacturing processes, welding, electroplating, pickling, and galvanizing can introduce hydrogen. Hydrogen embrittlement affects a broad spectrum of materials, predominantly those with high strength, high dislocation density, or microstructural features conducive to hydrogen trapping. Understanding the susceptibility of specific materials helps in designing mitigation strategies, selecting appropriate materials for hydrogen environments, and implementing suitable processing and protective measures. Hydrogen embrittlement or heat damage mechanisms. Critical factors based on API 571. Number A, 3 conditions must be satisfied. Number 1, hydrogen must be present at a critical concentration within the steel/alloy. Number 2, the strength level and microstructure of the steel/alloy must be susceptible to embrittlement. Number 3, a stress above the threshold for He must be present from residual stresses and/or applied stresses. Number B, the hydrogen can come from, number 1, welding. If wet electrodes or high moisture content flux weld electrodes are used, hydrogen can be charged into the steel, delayed cracking. Number 2, cleaning and pickling in acid solutions. Number 3, service in high-temperature hydrogen gas atmospheres. Molecular hydrogen dissociates to form atomic hydrogen that can diffuse into the steel. Number 4, wet H2S services or HF acid services in which atomic hydrogen diffuses into the steel. Cyanides, arsenic and FeS can act as hydrogen recombination poisons that diminish the hydrogen gas reaction and allows for greater charging rates. Number 5, manufacturing, melting practices or manufacturing processes particularly where components are plated, hydrogen flaking. Number 6, cathodic protection. Number C, the effect is pronounced at temperatures from ambient to about 300 degrees Fahrenheit 149 degrees Celsius. Effects decrease with increasing temperature. Number D, he affects static properties to a much greater extent than impact properties. If the hydrogen is present and a sufficient stress is applied, failure can occur quickly. Number E, the amount of trapped hydrogen depends on the environment, surface reactions, and the presence of hydrogen traps in the metal such as imperfections, inclusions and pre-existing flaws or cracks. Number F, the amount of hydrogen needed to have a measurable effect on the mechanical properties varies with the strength level, microstructure, and heat treatment for the alloy. In some cases, thresholds of critical hydrogen concentrations have been established. Number G, stresses include cooling during manufacture, residual stresses from welding or applied loads. Number H, thick wall components are more vulnerable due to increased thermal stress and high restraint and take longer for hydrogen to diffuse out. Number I, in general, as strength increases, susceptibility to heat increases. Certain microstructures, such as untempered martensite and perlite, are more susceptible at the same strength level than tempered martensite. Carbon steel that is severely hydrogen charged will have lower toughness than with no hydrogen. Here's a detailed explanation of the critical factors influencing hydrogen embrittlement or heat damage. Hydrogen embrittlement is a complex phenomenon influenced by multiple interconnected factors. These factors determine whether hydrogen will cause damage to a specific material under certain conditions. Understanding these critical factors is essential for predicting, preventing, or mitigating heat in engineering applications. Critical factors of hydrogen embrittlement damage includes, number 1, hydrogen availability and source, includes, number A, hydrogen concentration. The amount of diffusible atomic hydrogen present within the material directly impacts heat susceptibility. Higher hydrogen concentrations increase the likelihood of microstructural interactions leading to embrittlement. Sources of hydrogen concentration include manufacturing processes, welding, electroplating, pickling, corrosion reactions such as cathodic reactions in electrochemical environments, environmental exposure, hydrogen gas atmospheres, operational factors, pressure, temperature. Number B of hydrogen availability and source is hydrogen entry pathways, surface defects, microcracks, or porosity facilitate hydrogen ingress. Surface contamination or coatings can either hinder or promote hydrogen absorption. Critical factors of hydrogen embrittlement damage. Number 2 is mechanical stress conditions. Number A, applied tensile stress. External tensile stresses or residual stresses significantly influence heat. Stress increases the driving force for crack initiation and propagation. Critical stress levels, threshold stresses, exist below which he may not cause failure. Exceeding these can induce embrittlement. Number B of mechanical stress conditions is stress concentrations. Notches, welds, microvoids, or inclusions create localized stress razors. These regions are more susceptible to hydrogen-induced crack initiation. Number C of mechanical stress conditions is residual stresses. Stresses retained within the material from manufacturing, welding, or surface treatments can predispose the material to HE. Critical factors of hydrogen embrittlement damage. Number 3 is microstructural features, includes, number A, grain boundaries. Boundaries act as preferential sites for hydrogen accumulation. Weakened grain boundary cohesion can lead to intergranular cracking. Number B, dislocation density. High dislocation densities trap hydrogen atoms. Dislocations can serve as pathways or traps for hydrogen diffusion. Microstructural features. Number C, inclusions and microvoids. Non-metallic inclusions or porosity can concentrate hydrogen. Microvoids can coalesce into microcracks under stress. Microstructural features. Number D, microstructure type. Microstructures with microvoids, microcracks, or high dislocation densities are more vulnerable. Critical factors of hydrogen embrittlement damage. Number 4 is material properties, includes, number A, mechanical strength. Higher strength and hardness correlate with increased heat susceptibility. Materials with tensile strength above 1000 MPa are particularly vulnerable. Material properties. Number B, ductility and toughness. Low ductility reduces the ability to accommodate microcrack growth. Brittle materials are more prone to catastrophic failure. Material properties. Number C, cohesive strength. The intrinsic bonding strength between atoms influences how easily cracks can initiate and propagate. Critical factors of hydrogen embrittlement damage. Number 5 is environmental factors, includes, number A, presence of hydrogen-generating environments. Environments such as acidic solutions, cathodic protection systems, or moist atmospheres produce or facilitate hydrogen entry. Number B of environment factors is temperature. Elevated temperatures can increase hydrogen diffusivity. Specific temperature ranges may promote hydride formation, e.g., in titanium, exacerbating embrittlement. Conversely, very high temperatures may allow hydrogen to escape, reducing risk. Number C of environment factors is pH and electrochemical conditions. Acidic or corrosive environments accelerate hydrogen evolution and ingress. Critical factors of hydrogen embrittlement damage. Number 6 is processing and manufacturing conditions, includes, number A, welding and heat treatment. Welding introduces residual stresses and microstructural changes. Post-weld cooling can trap hydrogen. Heat treatments can reduce residual stresses or alter microstructure to mitigate HE. Number B, surface treatments. Electroplating, pickling, or passivation can introduce or trap hydrogen. Critical factors of hydrogen embrittlement damage. Number 7 is time and exposure duration. Prolonged exposure to hydrogen-rich environments or sustained stresses increases cumulative damage. Time-dependent diffusion allows hydrogen to penetrate deeper, increasing embrittlement risk. Critical factors of hydrogen embrittlement damage. Number 8 is critical thresholds and conditions, includes, number A, threshold stress intensity factors. A critical stress intensity factor or threshold stress exists below which He-induced cracking is unlikely. Exceeding these thresholds makes materials more prone to embrittlement. Number B, critical hydrogen concentration. A specific hydrogen concentration level may be necessary before embrittlement occurs. Below this, the material remains unaffected. The critical factors of hydrogen embrittlement are interconnected. The presence of hydrogen alone does not guarantee damage. Instead, damage occurs when hydrogen interacts with specific microstructural, mechanical, and environmental conditions that favor crack initiation and growth. A comprehensive understanding and control of these factors are essential for preventing He-related failures in susceptible materials and components. Hydrogen embrittlement damage affected units or equipment based on API 571. Number A, services where He is a concern include carbon steel piping and vessels in wet H2S services in FCC, hydroprocessing, amine, sour water services and HF alkylation units. However, mild steel used for vessels and piping in most refining, fossil utility and process applications have low hardness and are usually not susceptible to He except at weldments, particularly the HAZ, if suitable PWHT is not performed. Number B, storage spheres are often made of slightly higher strength steels and are more susceptible than most other refinery equipment. Number C, bolts and springs made of high-strength steel are very prone to He. Alloys that have a tensile strength above 150 ksi can absorb hydrogen during electroplating and crack. Number D, CRMO reactors, drums and exchanger shells on hydroprocessing units and catalytic reforming units are susceptible if the weld heat-affected zone hardness exceeds 235 bhn. Here's a detailed explanation of the units or equipment affected by hydrogen embrittlement or HE damage. Hydrogen embrittlement can compromise the structural integrity, safety, and functionality of a wide range of industrial equipment and units, especially those operating in hydrogen-rich environments or subjected to processes that introduce hydrogen into materials. Affected units and equipment in hydrogen embrittlement damage includes, number 1 is pipelines and storage systems, includes, number A, it using for hydrogen transportation pipelines. These pipelines designed to transport hydrogen gas or hydrogen-containing mixtures. These hydrogen transportation pipelines' vulnerable aspects includes, hydrogen ingress leads to embrittlement of steel or alloy pipes, cracks and failures can occur, risking leaks, explosions, or catastrophic rupture. These hydrogen transportation pipelines' impact includes, loss of containment, safety hazards and environmental risks. Pipelines and storage systems. Number B, it using for natural gas and oil pipelines. These pipelines transporting hydrocarbons where hydrogen can be produced internally via corrosion or cracking. These natural gas and oil pipelines' vulnerable aspects includes, internal corrosion can generate hydrogen, embrittlement causes cracking and leaks. Pipelines and storage systems. Number C, it using for storage tanks and vessels. Tanks storing hydrogen or other gases. Storage tanks and vessels' vulnerable aspects includes, hydrogen permeation into tank walls leading to embrittlement, potential for rupture or leakage. Number 2 of affected units and equipment in hydrogen embrittlement damage is pressure vessels and reactors, includes, number A, it using for hydrogen storage vessels. These high-pressure tanks, such as compressed hydrogen cylinders, cryogenic tanks, these hydrogen storage vessels' vulnerable aspects includes, hydrogen ingress causes embrittlement, reducing strength, risk of sudden failure during pressure cycles. Number B, it using for chemical reactors and process vessels. These equipment involved in hydrogen production, such as reformers, electrolyzers, chemical synthesis, or other reactions, these chemical reactors and process vessels' vulnerable aspects includes, hydrogen exposure leads to microcracking, especially in high-strength steels or alloys used internally. Number 3 of affected units and equipment in hydrogen embrittlement damage is welding and fabrication equipment. These tools and machinery used in welding, cutting, or surface treatments. These welding and fabrication equipment vulnerable aspects includes introduction of hydrogen during welding can cause HE in the weld zone or heat affected zone, equipment failure or cracks at welds if not properly managed. Number 4 of affected units and equipment in hydrogen embrittlement damage is mechanical components in hydrogen environments, includes, number A, it using for fasteners and bolts. These bolts, nuts, and threaded fasteners used in joints. These fasteners and bolts vulnerable aspects, includes, hydrogen-induced cracking can weaken the fasteners, leading to joint failure. Number B, it using for springs and high-strength components. These springs, shafts, or other high-strength parts subjected to tensile stresses. These fasteners and bolts vulnerable aspects, includes, embrittlement reduces ductility and load-bearing capacity. Number 5 of affected units and equipment in hydrogen embrittlement damage is nuclear reactor components, zirconium alloys. These zirconium-based cladding and components used in nuclear reactors. These nuclear reactor components vulnerable aspects, includes, hydride formation causes embrittlement, risking crack propagation, critical for safety and containment. Number 6 of affected units and equipment in hydrogen embrittlement damage is aerospace and marine equipment, includes, number A, it using for aircraft fuselage and structural components. These high-strength aluminum alloys and titanium parts, these aircraft fuselage and structural components vulnerable aspects, includes, hydrogen ingress during manufacturing or service leads to embrittlement, reducing fatigue life. Number B, it using for marine propellers and shafts. These components exposed to hydrogen-producing corrosion or manufacturing processes. These marine propellers and shafts vulnerable aspects, includes, embrittlement causes cracking and potential failure. Number 7 of affected units and equipment in hydrogen embrittlement damage is chemical processing equipment, includes, number A, it using for reactors, heat exchangers, and pumps. These equipment handling or exposed to hydrogen or hydrogen-generating chemicals. These reactors, heat exchangers, and pumps vulnerable aspects, includes, hydrogen ingress causes embrittlement, corrosion, and failure. Number B, it using for electrolyzers. These devices used for hydrogen production via electrolysis. These electrolyzers vulnerable aspects, includes, hydrogen permeation and embrittlement of internal components. Number 8 of affected units and equipment in hydrogen embrittlement damage is power generation equipment, includes, number A, it using for turbines and generators. These components exposed to hydrogen in fuel or cooling systems. These turbines and generators vulnerable aspects, includes, embrittlement can reduce fatigue life and cause cracks. Number B, it using for fuel cells. These devices converting hydrogen to electricity. These fuel cells vulnerable aspects, includes, hydrogen permeation can lead to degradation of internal parts. Hydrogen embrittlement can affect almost any equipment exposed to hydrogen or hydrogen-generating environments, especially those under stress or with microstructural vulnerabilities. The damage can lead to leaks, cracks, catastrophic failures, and safety hazards across industries such as energy, aerospace, chemical processing, and nuclear power. Preventive measures include selecting appropriate materials, controlling hydrogen exposure, applying protective coatings, and designing for reduced residual stresses. Hydrogen embrittlement appearance or morphology of damage based on API 571, number A, cracking due to he can initiate subsurface, but in most cases is surface breaking, see Figure 4-160A, cracking due to hydrogen embrittlement of a carbon steel tube. See Figure 4-160B, intergranular crack emanating from surface in the tube. See Figure 4-161A, hydrogen embrittlement of martensitic SS pump parts. See Figure 4-161B, high magnification photomicrograph of fracture surface showing intergranular nature of cracking. Number B, HE occurs at locations of high residual or triaxial stresses, notches, restraint, and where the microstructure is conducive, such as in weld HAZs. Number C, on a macro scale, there is often little evidence, although some materials will appear to have brittle fracture surfaces. On a microscale, the material will contain less ductile fracture surface, but must often be compared to a fracture without the presence of hydrogen. Number D, in higher strength steels, cracking is often intergranular. Here's a detailed explanation of the appearance and morphology of hydrogen embrittlement or heat damage. Hydrogen embrittlement manifests through distinct microstructural features and surface indications that reflect the underlying damage mechanisms caused by hydrogen interactions within the material. Recognizing these features is crucial for diagnosing HE-related failures and understanding the damage progression. Appearance and morphology of hydrogen embrittlement or heat damage includes, number 1, surface features, includes, number A, cracks. This cracks predominantly intergranular, along grain boundaries, or transgranular, through grains, depending on the material and stress conditions. The appearance of this cracks are, fine, hairline cracks often visible under a microscope. Cracks may be branched or coalesced. They frequently originate at surface defects such as inclusions, microvoids, or stress concentrators. In severe cases, cracks can propagate to form macrocracks visible to the naked eye. Number B of surface features is blistering and delamination. This is a formation of blisters or bubbles on the surface. The appearance of this blistering and delamination are elevated or blistered areas caused by hydrogen gas accumulation beneath the surface, often associated with localized delamination or spallation of surface layers, common in coatings or thin films exposed to hydrogen. Number C of surface features is surface dimpling or pitting. This is a microvoid formation leading to surface pitting. The appearance of this surface dimpling or pitting are small, crater-like pits or dimples, result of microvoid coalescence and crack initiation points. Appearance and morphology of hydrogen embrittlement or heat damage. Number 2 is microstructural features, includes, number A, microcracks. The location of microcracks appears commonly, frequently aligned along grain boundaries, intergranular cracking, or within the grains, transgranular cracking, The appearance of this microcracks are very fine, often requiring microscopy, optical or SEM, to resolve, may be branched or exhibit a network pattern, can be visible as dark lines or fissures within the microstructure. Microstructural features. Number B, hydride or hydride precipitate formation, in susceptible alloys. The appearance of these features are needle-shaped or plate-like hydrides within the microstructure, typically occur in zirconium alloys or titanium, where hydrogen reacts with metal to form brittle hydrides. These precipitates are visible under microscopy and are associated with embrittlement zones. Microstructural features. Number C is microvoids and microcracks. Its formation are, microvoids form at inclusions, grain boundaries, or dislocation pileups. Coalescence of microvoids leads to microcracks. The appearance of these microvoids and microcracks are small, spherical or irregular voids in the microstructure, often observed via transmission electron microscopy, TM, or focused ion beam, FIB, imaging. Appearance and morphology of hydrogen embrittlement or heat damage. Number 3 is internal damage features, includes, number A, intergranular fracture. The appearance of this intergranular fracture are, fracture surfaces show a network of cracks along grain boundaries. The fracture surface appears faceted or granular, indicates that hydrogen has weakened the grain boundary cohesion. Internal damage features. Number B, transgranular fracture. The appearance of this transgranular fracture are, cracks cut across grains, with a more ductile or brittle fracture surface, often exhibits cleavage facets or striations. Internal damage features. Number C, microvoid coalescence. The appearance of this microvoid coalescence are, numerous microvoids or cavities within the material coalescing into cracks, seen in fracture surfaces as dimples or rough regions. Appearance and morphology of hydrogen embrittlement or heat damage. Number 4 is fracture surface morphology, includes, number A, brittle fracture features. The appearance of this brittle fracture features are, smooth, shiny fracture surfaces with cleavage facets, lack of plastic deformation features, often called flat fracture surfaces. Internal damage features. Number B, ductile fracture features. The appearance of this ductile fracture features are, dimpled fracture surfaces indicating plastic deformation, less common in HE-damaged materials but can occur under certain conditions. Internal damage features. Number C, mixed mode fracture. The appearance of this mixed mode fracture are, features both brittle and ductile characteristics, with regions of cleavage and dimpled areas. Internal damage features. Number B, ductile fracture features. The appearance of this ductile fracture features are dimpled fracture surfaces indicating plastic deformation, less common in HE-damaged materials but can occur under certain conditions. Internal damage features number C, mixed mode fracture. The appearance of this mixed mode fracture features both brittle and ductile characteristics, with regions of cleavage and dimpled areas. Hydrogen embrittlement damage exhibits characteristic morphologies mainly characterized by surface cracks, intergranular or transgranular, microvoids and microcracks within the microstructure, hydride formations in specific alloys, blistering and blister-like features on the surface, fracture surfaces showing brittle features such as cleavage facets or a granular appearance. The appearance varies depending on the material, the environment, the stress state, and the severity of hydrogen. Ingress. Microstructural examination using optical microscopy, SEM, scanning electron microscopy, TEM, or fractography is essential for identifying and diagnosing HE damage. Hydrogen embrittlement or HE damage prevention and mitigation based on API 571, number A, dependent on the source of the hydrogen, alloy composition and fabrication/heat treatment history. Number B, use lower strength steels and PWHT to temper the microstructure, improve ductility and reduce residual stresses and hardness. Number C, during welding, use low hydrogen, dry electrodes and preheating methods. If hydrogen is expected to have diffused into the metal, an elevated temperature bake out, 400 degrees Fahrenheit or higher, 204 degrees Celsius or higher, may be required to drive the hydrogen out prior to welding. Number D, heavy wall equipment in hot hydrogen service requires controlled shutdown and startup procedures to control the pressurization sequence as a function of temperature. Number E, in corrosive aqueous surfaces, apply a protective lining, SS cladding, or weld overlay to prevent the surface hydrogen reactions. Here's a comprehensive and detailed explanation of prevention and mitigation strategies for hydrogen embrittlement or HE damage. Hydrogen embrittlement poses significant risks to structural integrity and safety in various industries. Therefore, implementing effective prevention and mitigation measures is critical. These strategies encompass material selection, process controls, protective coatings, environmental controls, and maintenance practices. Prevention and mitigation of hydrogen embrittlement or HE damage includes, number 1, material selection and design, includes, number A, use of hydrogen-resistant materials. For the first example is alloys and steels, select materials with high resistance to HE, such as austenitic stainless steels, nickel-based alloys, or brittle-resistant high-strength steels. Avoid high-strength, quenched, or tempered steels that are more susceptible. For the second example is microstructure optimization, use materials with refined grain sizes, uniform microstructures, and minimal inclusions. Reduce microvoids, internal defects, and impurity levels that act as hydrogen trapping sites. Number B of material selection and design is material treatments, includes, for the first example is heat treatments, apply appropriate heat treatments, annealing, normalizing, to reduce residual stresses and improve ductility. For the second example is surface treatments, employ processes such as carboizing, shot peening, or surface alloying to enhance surface toughness and reduce hydrogen ingress. Prevention and mitigation of hydrogen embrittlement or HE damage. Number 2 is control of environmental factors, includes, number A, minimize hydrogen exposure, the first of it by use of inert atmospheres. During welding, manufacturing, or processing, use inert gases, argon, nitrogen, to prevent hydrogen absorption. The second of minimize hydrogen exposure is control of moisture and contaminants, reduce exposure to moisture, acids, or other sources of hydrogen-generating chemicals. The third of minimize hydrogen exposure is proper handling of hydrogen-containing materials. Store and transport materials in low hydrogen environments. Number B of control of environmental factors is management of hydrogen sources, includes, the first is corrosion control, use corrosion inhibitors or coatings to prevent hydrogen generated during corrosion. For the second of management of hydrogen sources is electrochemical control, apply cathodic protection carefully since overprotection can promote hydrogen evolution. Prevention and mitigation of hydrogen embrittlement or HE damage. Number 3 is process and manufacturing controls, includes, number A, welding and heat treatment, the first of it by use of low hydrogen welding techniques, use low hydrogen electrodes and welding procedures. Maintain proper preheating and post-weld heat treatment to reduce hydrogen entrapment. The second of welding and heat treatment is minimize heat-affected zone or HAZ toughness loss, proper control of welding parameters to prevent microstructure changes that increase susceptibility. The third of welding and heat treatment is post-weld heat treatment, conduct stress relief annealing or baking, such as at 150 through 200 degrees Celsius for several hours, to drive out residual hydrogen. Number B of process and manufacturing controls is surface preparation, includes, the first is cleaning, remove surface contaminants, oxides, and residual flux that could trap hydrogen. For the second of surface preparation is coatings and barrier layers, apply protective coatings, such as paint, polymer, or metallic coatings, to prevent hydrogen ingress. Prevention and mitigation of hydrogen embrittlement or HE damage. Number 4 is protective coatings and barriers, includes, number A, hydrogen impermeable coatings. Use coatings such as epoxy, rubber, or metallic barriers to physically block hydrogen permeation. Number B, cathodic protection with care, optimize cathodic protection to prevent hydrogen evolution without promoting embrittlement. Prevention and mitigation of hydrogen embrittlement or HE damage. Number 5 is design considerations, includes, number A, stress minimization. Design components to minimize tensile residual stresses and operational stresses. Use stress relief features or smooth geometries to reduce stress concentrations. Number B of design considerations is avoid sharp corners and notches, reduce localized stress points that facilitate crack initiation. Number C of design considerations is allow for stress redistribution, incorporate features facilitating uniform stress distribution. Prevention and mitigation of hydrogen embrittlement or HE damage. Number 6 is operational and maintenance practices, includes, number A, regular inspection. Conduct periodic non-destructive testing or NDT such as ultrasonic testing, dye penetrant, or radiography to detect early signs of HE damage. Use fractography to analyze fracture surfaces if failures occur. Number B of operational and maintenance practices is control of operating conditions. Limit operational stresses, especially cyclic or tensile stresses. Control temperature to avoid conditions conducive to hydrogen diffusion and trapping. Number C of operational and maintenance practices is post-exposure treatments. Perform baking at appropriate temperatures after welding or exposure to hydrogen environments to remove absorbed hydrogen. Employ stress relief annealing where applicable. Prevention and mitigation of hydrogen embrittlement or HE damage. Number 7 is use of inhibitors and additives. In certain chemical environments, additives or inhibitors can reduce hydrogen generation or absorption, for example, adding corrosion inhibitors or passivating agents to suppress hydrogen evolution. Prevention and mitigation of hydrogen embrittlement or HE damage. Number 8 is monitoring and real-time control, includes, number A, hydrogen sensors, install sensors to monitor hydrogen levels in critical environments. Number C, residual stress measurement, use techniques such as X-ray diffraction or XRD to measure residual stresses and implement corrective measures as needed. Preventing and mitigating hydrogen embrittlement requires a holistic approach integrating material science, engineering design, fabrication practices, environmental controls, and maintenance. The key is to reduce hydrogen ingress, minimize internal and residual stresses, and use suitable materials and protective measures to sustain the integrity of components exposed to hydrogen environments. Hydrogen embrittlement or HE damage inspection and monitoring based on API 571. Number A, for surface cracking inspection use PT, MT, or WFMT. Number B, UT may also be useful in finding HE cracks. Number C, RT often is not sufficiently sensitive to detect HE cracks. Number D, if the source of hydrogen is a low-temperature aqueous environment, hydrogen flux can be monitored using specialized instruments. Here's a detailed explanation of inspection and monitoring methods used to detect hydrogen embrittlement damage. Hydrogen embrittlement is a subtle and progressive form of material degradation that often manifests at the microstructural level before catastrophic failure occurs. Detecting HE early requires specialized inspection techniques capable of revealing microstructural changes, cracks, or internal damage caused by hydrogen. Below are the primary methods, their principles, advantages, limitations, and typical applications. Inspection and monitoring methods for detecting hydrogen embrittlement or HE damage. Number 1 is visual inspection. This is the most basic inspection method, involves careful examination of the component's surface for visible signs such as cracks, blistering, or surface pitting. Application visual inspection is suitable for components with accessible surfaces, often combined with magnification tools, such as magnifying glasses, borescopes. Limitation of visual inspection is, cannot detect subsurface or microstructural heat damage, less effective for early stage or microcrack detection. Inspection and monitoring methods. Number 2 is dye penetrant testing or DPT. Its principle is use a liquid dye applied to the surface to penetrate surface-breaking cracks or flaws. After removing excess dye, a developer is applied to draw out the dye from flaws, making cracks visible. Application dye penetrant testing is to detect surface microcracks and flaws associated with HE. It is suitable for inspecting welds, surface cracks, and blistered areas. Dye penetrant testing advantages includes simple and cost-effective, enhances surface crack detection sensitivity. Dye penetrant testing limitations includes only detects surface or near-surface flaws, cannot reveal subsurface damage or internal microcracks. Inspection and monitoring methods. Number 3 is ultrasonic testing or UT. Its principle is use high-frequency sound waves transmitted into the material. Cracks or defects reflect these waves back, which are detected by a receiver. Application ultrasonic testing is to detect internal cracks, voids, or delaminations associated with HE, suitable for thick components and complex geometries. Ultrasonic testing advantages includes capable of detecting subsurface damage, quantitative assessment of flaw size. Ultrasonic testing limitations includes requires skilled operators, resolution limits for very small microcracks, material-specific calibration needed. Inspection and monitoring methods. Number 4 is radiographic testing or RT. Its principle is uses X-rays or gamma rays to produce images of internal structures. Flaws such as cracks or voids appear as regions of differing density. Application radiographic testing is to detect internal microvoids, crack networks, or delamination. Radiographic testing advantages includes provides a permanent record, detects internal damage not visible on surface. Radiographic testing limitations includes less sensitive to small microcracks, requires safety precautions and shielding, limited resolution for very fine cracks. Inspection and monitoring methods. Number 5 is microstructural and fractographic analysis, includes, number A, optical microscopy. It uses to examines polished and etched samples. Reveals microcracks, hydride precipitates, or microvoids. Number B of microstructural and fractographic analysis is scanning electron microscopy or SEM, provides high-resolution imaging of fracture surfaces and microstructural features. Can identify intergranular versus transgranular cracking patterns. Number C of microstructural and fractographic analysis is transmission electron microscopy or TEM. It uses for atomic scale analysis. Detects hydride precipitates and microstructural changes at the nanoscale. Microstructural and fractographic analysis applications includes critical for research, failure analysis, and understanding He mechanisms. Useful for early detection of microstructural damage. Microstructural and fractographic analysis limitations includes destructive sampling, requires specialized equipment and expertise. Inspection and monitoring methods. Number 6 is acoustic emission monitoring. Its principle is detects transient elastic waves generated by crack initiation and propagation. Can monitor active damage processes in real time. Application acoustic emission monitoring is suitable for detecting the onset of crack growth due to HE, effective during operational loading to identify active damage. Acoustic emission monitoring advantages includes real-time monitoring, can cover large areas. Acoustic emission monitoring limitations includes sensitive to environmental noise, requires sophisticated data analysis. Inspection and monitoring methods. Number 7 is residual stress measurement. Its methods are includes X-ray diffraction or XRD is a non-destructive method to measure surface residual stresses. Hole drilling method is a semi-destructive technique to measure internal stresses. Residual stress measurement relevance for residual tensile stresses promote heat crack initiation. And monitoring residual stresses helps assess susceptibility. Inspection and monitoring methods. Number 8 is hydrogen measurement techniques, includes, number A, hydrogen content analysis, thermal desorption spectroscopy or TDS, quantifies hydrogen trapped within the material. Hot vacuum extraction, measures hydrogen released upon heating, number B, surface hydrogen detection. Electrochemical hydrogen sensors, detect hydrogen permeating to the surface during operation. The application of hydrogen measurement techniques is to determine hydrogen levels correlating with embrittlement risk. Early detection of HE damage relies on combining multiple methods, surface inspections, visual, dye penetrant, for initial screening, non-destructive internal methods, ultrasound, radiography, for subsurface damage, microstructural analysis, microscopy, for detailed understanding, monitoring residual stresses and hydrogen levels to evaluate susceptibility. Operational strategies include regular inspections, especially after welding, high-stress operation, or hydrogen exposure events. Proactive monitoring, e.g., acoustic emission, during operation can provide real-time alerts for active crack growth. Thank you.